Hello, and welcome to the Sleepy Curiosity channel. As you find a comfortable position, let your body start releasing the weight of the day. If this gentle journey is already beginning to slow your thoughts, consider subscribing now, so these stories can keep finding you night after night. Now, let the relaxation settle into your breathing. There's a moon in the solar system where liquid methane rains down over lakes of ethane. There's another where volcanoes cover the entire surface in continuous lava, without a single visible crater. There's a planet that orbits the Sun almost lying on its side, with poles that spend 42 years in full daylight and another 42 years in total darkness. None of these worlds had to be this way, and the fact that they are reveals more about planetary physics than decades of theory managed on their own. And the deeper we go, the more surprising it becomes. The solar system didn't come from nothing, it was born from the collapse of a cloud of gas and dust that already carried within it the history of dead stars. About 4.6 billion years ago, a region of the Milky Way contained a cold, dense molecular cloud, made up mainly of hydrogen and helium, but also of heavier elements forged in earlier supernovae. Something disturbed that cloud, possibly the shockwave from a nearby supernova, and gravitational collapse began. Not slowly, not gently, with the irreversible urgency of everything that falls toward its center. As the cloud collapsed, it spun. And the more it collapsed, the faster it spun, by the same principle that accelerates a skater when they pull their arms in. That spin prevented all the mass from falling directly to the center, most of it accumulated in a flat, rotating disk around the forming protosun. That disk, called the protoplanetary disk or solar nebula, was the birthplace of everything that exists in the solar system today. From the planets to the asteroids, from the comets to the moons, from interstellar dust grains to the oceans that cover the Earth. Modern telescopes have already photographed protoplanetary disks around hundreds of young stars in our galaxy, structures that look exactly like what models predict for the early solar system. We're watching, in real time, solar systems forming around other stars. Ours went through the same process, and the evidence of that birth is preserved in the oldest and most primitive objects in the system, meteorites that date back 4.567 billion years with a precision of just a few million years. Inside the protoplanetary disk, matter didn't organize itself uniformly. Temperature varied dramatically with distance from the protosun. In the inner regions, only materials with high melting points could solidify. Water, methane, ammonia, and other volatile compounds could only exist in solid form beyond a certain distance from the young sun. That boundary is called the snow line, and it was one of the most defining factors in the difference between the inner and outer planets. Inside the snow line, the available solid grains were few and heavy, rocky and metallic materials. The planets that formed in that region are small and dense: Mercury, Venus, Earth, and Mars. Beyond the snow line, there was much more material available, not just rock, but enormous quantities of water, ice and other compounds. The rocky cores that formed in that region grew quickly and, upon reaching a critical mass, began capturing gas directly from the disk, becoming the gas and ice giants we know today. The snow line boundary wasn't just a temperature line, it was the boundary between two completely different types of world. The formation of the planets was not a smooth and gradual process, it was chaotic, violent and probabilistic. The first stage was the sticking together of microscopic dust grains into larger aggregates. These aggregates grew into planetesimals, rocky bodies ranging from meters to kilometers, and the planetesimals collided and merged into larger bodies called protoplanets. This accretion process was competitive. Larger bodies had more gravity, attracted more material and grew faster, while smaller bodies were absorbed or ejected. The meteorites that reach Earth today are, for the most part, fragments of planetesimals that never grew large enough to become planets, remnants of the formation process preserved in orbit for 4.6 billion years. Each meteorite is a time capsule, a fragment of a world that almost existed. Some contain presolar grains, particles formed in stars that existed before the Sun, survived the formation of the system and were incorporated into asteroids that eventually reached Earth. They are, literally, dust from stars older than the Sun, preserved in rocks that fell here. One of the most important events in the history of the young solar system was called the Grand Instability, a period of dramatic gravitational reorganization that occurred a few 100 million years after the planets formed. Models suggest that the gas giants didn't form in the orbits they're in today. Jupiter, Saturn, Uranus and Neptune would have formed closer together and closer to the Sun. The gravitational interaction with a disk of remaining planetesimals caused a slow migration of the giants' orbits, and at a certain point, Jupiter and Saturn reached an orbital resonance that triggered a cascading instability. This reorganization had catastrophic and paradoxically constructive consequences. The planetesimal disk was disrupted in such a way that a rain of asteroids and comets bombarded the inner planets, an event called the Late Heavy Bombardment, which left the surfaces of the Moon and Mars marked with the craters we see today. But that same rain may have delivered to Earth significant quantities of water and organic compounds, ingredients that may have been essential for the emergence of life. The chaos that destroyed also created. The question of the origin of Earth's water is one of the most active debates in cosmochemistry today. The isotopic ratios of hydrogen in ocean water match more closely those of certain types of asteroids than those of comets that have been studied. This suggests that asteroids, more than comets, were the main suppliers of water to Earth, though comets may have contributed a fraction. The ocean that covers 71% of Earth's surface was, to a large extent, delivered by rocky bodies that traveled from regions beyond the snow line. The water you drink has a history that begins beyond Mars. The Sun consumed most of the mass of the protoplanetary disk, but not just through passive gravitational accretion. The young Sun was much more active than it is today. In the first tens of millions of years, it went through a phase called T Tauri, characterized by intense stellar winds, frequent flares and variable luminosity. That early solar wind was much stronger than the current one, and it was what swept away the remaining gas from the protoplanetary disk, bringing the formation of the giant planets to an end. The timing of that event was crucial. If the Sun had dispersed the gas disk earlier, Jupiter and Saturn wouldn't have had time to capture their enormous atmospheres. If it had dispersed it later, the giants could have migrated even closer to the Sun, as happened in many other stellar systems where gas giants exist in very close orbits around their star. The fact that our Jupiter is where it is, and not where a typical hot Jupiter is, may be one of the reasons why Earth exists the way it does. The stability of our home depends on details that played out more than 4 billion years ago. The Moon is one of the most studied objects outside Earth, and its origin was, for a long time, one of the greatest mysteries in planetary science. The hypothesis that today has broad support is the giant impact, about 4.5 billion years ago, a protoplanet roughly the size of Mars, called by scientists Theia, collided with the proto-Earth at an oblique angle. The impact was colossal enough to partially melt both bodies, vaporizing enormous quantities of rock and launching a cloud of debris into orbit around Earth. That cloud condensed and accumulated, forming the Moon. The most powerful evidence for this hypothesis is isotopic composition. The Moon and Earth have remarkably similar oxygen and titanium compositions, more similar to each other than between Earth and any other body in the solar system. The giant impact mixed the materials of Theia and the proto-Earth thoroughly enough to produce the similarity we observe. And it also explains why the Moon is relatively poor in volatile elements, which would have been vaporized in the impact. The Moon is, literally, a scar from the greatest collision Earth ever suffered. The solar system is approximately 4.6 billion years old, and that's not a vague estimate. It's a measurement based on decades of radiometric analyses of meteorites, lunar rocks and terrestrial samples, using multiple radioactive decay systems that agree with each other with remarkable precision. The oldest known terrestrial mineral, a zircon grain from Jack Hills, in Australia, is 4.4 billion years old. Lunar rocks brought back by the Apollo missions are up to 4.5 billion years old. What is equally remarkable is that 4.6 billion years is only 1/3 of the age of the universe. The universe had already existed for more than 9 billion years when the Sun ignited. Stars and planetary systems much older than ours exist in the galaxy, some 10 or 12 billion years old. If rocky planets form around old stars the same way they form around younger ones, then civilizations with billions of years of advantage over ours could exist in the Milky Way. And that thought is the starting point for one of the deepest questions ever posed by science. And there's a detail that changes everything when we think about the architecture of the solar system. A provocative hypothesis, called the Grand Tack, suggests that Jupiter migrated significantly inward during its formation, coming almost as close as Mars's current orbit, before being slowed and pulled back outward by Saturn. That back-and-forth migration of Jupiter would have swept material from the inner orbits, explaining why Mars is so small and why there are no super-Earths in the inner system. The existence of Earth as a planet of the right size for life may depend on the gravitational dance of Jupiter and Saturn at a very specific moment in the history of the system. The Sun is so dominant in the solar system that it's easy to treat it as background. But the Sun is a dynamic, complex, and constantly active object. It contains 99.86% of all the mass in the solar system. Jupiter, the second largest object, accounts for only 0.1%. All the planets, moons, asteroids and comets combined are a tiny fraction of what the Sun contains. At the center of the Sun is the core, a sphere where the temperature reaches 15 million degrees and the pressure is 250 billion times Earth's atmospheric pressure. That's the region where all the nuclear fusion that generates the Sun's energy takes place. Around the core is the radiative zone, where energy travels in the form of photons that are continuously absorbed and re-emitted, making their way through that tortuous path for tens of thousands of years before reaching the next layer. The light that left the Sun yesterday may have been created when the first modern humans inhabited the Earth. Above the radiative zone is the convective zone, a region where hot gas rises in large convection cells, transfers heat to the surface and sinks back down, like water boiling in a pot on a solar scale. That convection is visible on the Sun's surface as a granular texture called solar granulation, cells of bright gas about 1,000 kilometers in diameter, each existing for only a few minutes before dissolving and being replaced. The surface of the Sun is an ocean in eternal boil. Nuclear fusion in the solar core is remarkably inefficient on an individual level, which is, paradoxically, one of the reasons the Sun has been shining steadily for 4.6 billion years. For two protons to fuse, one of them needs to convert into a neutron, a process that involves the weak nuclear force, the slowest of the fundamental forces. The probability of this happening in any individual collision is extraordinarily low. Each proton in the solar core waits, on average, billions of years before taking part in a fusion reaction. What almost no one realizes is that this slowness has a profound consequence. If nuclear fusion were more efficient, the Sun would have burned through all its hydrogen in much less time, and life on Earth wouldn't have had time to develop. The slowness of the weak force is, indirectly, a condition for the existence of complex biospheres on rocky planets around stars like the Sun. The microscopic inefficiency of a nuclear reaction makes life possible on a planetary scale. One of the most unsettling discoveries in solar astrophysics was the solar neutrino problem. In the 1960s, physicist Raymond Davis built a neutrino detector in a deep mine and began counting the neutrinos coming from the Sun. The result was consistently about 1/3 of the number predicted by solar models. For decades, this created an uncomfortable tension: either the models of the solar interior were wrong, or there was something wrong with our understanding of neutrinos. The resolution came decades later, with the discovery that neutrinos oscillate. They change type during their journey. The Sun produces only electron-type neutrinos, but Davis's detector could only detect that type. Since the neutrinos oscillated between three flavors during their travel from the Sun to Earth, only 1/3 arrived still as electron neutrinos. When detectors capable of capturing all three flavors were built, the number agreed with solar predictions. That resolution proved that neutrinos have mass, and forced a revision of the standard model of particle physics. An anomaly in the Sun's particle count led to one of the most important discoveries in 20th century physics. The Sun's atmosphere has a peculiarity that has puzzled physicists for decades: it gets hotter as it moves away from the surface. The photosphere, the visible surface, is about 5,500 degrees Celsius. The chromosphere, above it, reaches tens of thousands of degrees. And the corona, the thin outer atmosphere that extends for millions of kilometers, has temperatures of 1 to 3 million degrees. This seems to violate basic thermodynamic intuition. How can a region farther from the heat source be hotter? This is the coronal heating problem, and it remains one of the greatest open problems in solar physics. The Sun's magnetic field is the engine behind almost all observable solar activity. Roughly every 11 years it goes through a complete cycle in which it intensifies, becomes tangled, and reverses. The Sun's magnetic poles swap places. At the peak of the cycle, the field becomes complex and knotted, with more numerous sunspots and more energetic events, solar flares and coronal mass ejections. The most intense event ever recorded occurred in September of 1859 and is known as the Carrington event. The coronal mass ejection reached Earth in just 17 hours and produced auroras visible as far as the Caribbean. Telegraphs failed across Europe and North America, with some operators reporting electric shocks and papers catching fire. If an event of equivalent magnitude were to occur today, the consequences for global technological infrastructure would be potentially catastrophic. Estimates suggest damages in the trillions of dollars. Studies of tree rings have revealed even more intense events in the past. The Sun is not just the source of life, it is also, occasionally, a threat. The solar wind is a continuous stream of charged particles that the Sun emits in all directions at speeds between 400 and 800 kilometers per second. That stream shaped each planet differently, depending on how each one responds to that constant bombardment. Earth is protected by its magnetosphere, the magnetic field generated by the liquid iron dynamo in its outer core. Without that protection, the solar wind would progressively erode Earth's atmosphere, exactly what happened to Mars, which lost its magnetic field about 4 billion years ago. The aurora borealis and australis are the most visible manifestation of the interaction between the solar wind and the magnetosphere. When energetic particles escape the magnetic defenses and enter the atmosphere through the polar regions, they excite oxygen and nitrogen molecules that emit light as they return to their ground state. The colors depend on the element and the altitude. Green and red come from oxygen, blue and violet from nitrogen. It's one of the most beautiful manifestations of plasma physics, and a constant reminder that the Sun is actively interacting with Earth at this very moment. The heliosphere is the bubble created by the solar wind, a region of space where solar plasma and magnetic field dominate over the interstellar medium. It extends well beyond Pluto. The boundary between the heliosphere and the interstellar medium is called the heliopause. In August of 2012, the Voyager 1 probe crossed that boundary, becoming the first human-made object to enter interstellar space. The probe was 18.1 billion kilometers from the Sun at that moment. Launched in 1977, it had taken 35 years to travel that distance. And it was still working. The 4 rocky planets of the solar system are Mercury, Venus, Earth and Mars, formed from the same protoplanetary disk, in the same region, with materials of similar composition. And yet they are radically different worlds from one another. Comparing the rocky planets is, in a certain sense, a natural experiment in planetary evolution with 4 samples. For possible trajectories for a rocky planet, and only one produced the life we know. Mercury is the planet closest to the Sun and, in several ways, the most extreme of the rocky planets. Its density is surprisingly high, the second highest in the solar system, just after Earth. That means Mercury has a disproportionately large iron core, estimated at about 85% of the planet's radius. The most widely accepted hypothesis is that Mercury suffered a giant collision in the early solar system that stripped away much of its original mantle, leaving the metallic core exposed in a much larger proportion than in other rocky planets. Mercury also has one of the most extreme temperature variations in the solar system. During the day, the surface facing the Sun can reach 430 degrees Celsius. During the long Mercurian night, a day on Mercury lasts 59 Earth days, the temperature drops to -180 degrees. And paradoxically, in Mercury's polar regions, where sunlight never directly penetrates the deep craters, there's evidence of water ice, preserved in permanent shadow just 77 million kilometers from the Sun. That shouldn't happen, but it does. Venus is often called Earth's twin. It has very similar size and mass, and formed in the same region of the protoplanetary disk. But it's one of the most hostile environments in the solar system. Atmospheric pressure at the surface is 92 times that of Earth, equivalent to the pressure 900 meters deep in Earth's ocean. The surface temperature is about 465 degrees Celsius, constant day and night, at the poles and at the equator. Venus is hotter than Mercury, despite being farther from the Sun, and the reason is a completely runaway greenhouse effect. The question of why Venus and Earth evolved so differently, despite their initial similarities, is one of the most important in planetary science. One hypothesis is that Venus, being closer to the Sun, heated up earlier and lost its water before it could dissolve atmospheric carbon dioxide into oceans. Without oceans, the carbon cycle never established itself. Carbon dioxide accumulated in the atmosphere and the greenhouse effect accelerated without control. Earth may have escaped that fate by a narrower margin than we usually imagine. And there's a detail that changes everything when we look at Venus with fresh eyes. Climate models published starting in 2016 suggest that Venus could have had liquid water oceans for up to 2 billion years, much longer than Mars maintained habitable conditions. If that's correct, Venus would have been an ocean world for much of the period during which life emerged on Earth. The closest hell to us may have been habitable for longer than we imagined. Mars is the most studied rocky planet beyond Earth. Its surface tells a story of dramatic transformation, evidence of rivers, lakes, and possibly oceans existing more than 3.5 billion years ago, followed by progressive cooling, loss of atmosphere, and freezing of water resources. What caused the transformation of Mars from a potentially habitable world into a cold, arid desert involves the loss of the Martian magnetic field. Mars cooled more quickly than Earth, its core solidified too early to maintain the liquid iron dynamo, and without that protection, the solar wind progressively eroded the atmosphere over billions of years. Mars has the tallest mountain in the solar system, Olympus Mons, a shield volcano 21.9 kilometers high and approximately 600 kilometers in diameter at its base. Olympus Mons is so wide that if you were standing in its crater at the top, the horizon would be beyond the edges of the mountain's base. You wouldn't be able to tell you were on a mountain. Its total extent would be enough to cover all of France. Mars also hosts the largest canyon in the solar system, Valles Marineris, a system of valleys stretching about 4,000 kilometers with up to 7 kilometers of depth and 200 kilometers of width at some points. For comparison, the Grand Canyon is 446 kilometers long and 1.8 kilometers deep. Valles Marineris was not formed by river erosion, but mainly by tectonic faulting. The Martian crust split apart along massive geological fault lines, creating a scar visible from space. The question of life on Mars remains open in ways that no mission has yet been able to definitively resolve. The current surface of Mars is hostile, intense radiation, absence of stable liquid water, oxidizing compounds in the soil. But the Martian subsurface may be a different story. In 2018, the radar on the Mars Express probe detected a signal consistent with a subglacial lake of liquid water beneath the south polar cap of Mars, at about 1.5 kilometers of depth. Later analyses identified additional signals, suggesting multiple bodies of water. The possibility of life in the Martian subsurface has not been ruled out by any mission to this day. Earth's crust is unique among the rocky planets for a feature that completely transforms the geology and chemistry of the planet: plate tectonics. Earth's lithosphere is divided into about 15 major plates that move over the partially molten mantle, creating mountain ranges where they collide, ocean trenches where one dives beneath the other, and underwater volcanic chains where they pull apart. No other rocky planet in the solar system has active plate tectonics. Plate tectonics is not just a geological phenomenon, it's a fundamental climate regulator. Earth's carbon cycle depends critically on the plates. Silicate rocks on the surface absorb carbon dioxide from the atmosphere through chemical weathering, form carbonates that are carried into the mantle through subduction, and the carbon is returned to the atmosphere through volcanism. This long-term carbon cycle is the planet's thermostat. When temperature rises, weathering accelerates, removes more carbon dioxide and cools the planet. When it gets too cold, the process reverses. It's a regulatory system that has been working for billions of years, and that no other planet in the solar system has. Earth's atmosphere is an anomaly in the context of rocky planets. The oxygen we breathe is almost entirely photosynthetic in origin, produced by billions of years of activity from cyanobacteria and plants. The Great Oxidation, which occurred about 2.4 billion years ago, was one of the most dramatic transformations in Earth's history. Before it, Earth's atmosphere was essentially free of molecular oxygen. Cyanobacteria, which evolved oxygenic photosynthesis, began releasing oxygen as a byproduct of their metabolism. For most organisms existing at the time, oxygen was a poison, highly reactive and lethal to anaerobic metabolisms. The Great Oxidation was possibly the greatest mass extinction in the history of life on Earth. But it also opened the way for a new era of more efficient metabolisms, for the evolution of complex cells and, eventually, for all the diversity of multicellular life that came after. The atmosphere that we take for granted in our daily experience is the cumulative product of billions of years of biological activity. The asteroid belt occupies a region between the orbits of Mars and Jupiter, and it's not a fragmented planet, as many imagine. It's material that never managed to become a planet. The reason no planet formed in that region is Jupiter. The gravity of the gas giant continuously disrupted the orbits of the planetesimals that were trying to accumulate in that region, increasing the collision speeds between them. Instead of slow collisions that allow for clumping, the collisions were too fast, the bodies fragmented instead of merging. Jupiter, in essence, prevented a planet from forming in its inner neighborhood. The result is a population of objects that varies enormously in size, composition, and history. Ceres and all the other objects in the belt combined have a total mass of only about 4% of the Moon's mass. The asteroid belt is remarkably empty. If you flew through it in a straight line, the statistical probability of colliding with any object would be extremely low. The images in movies showing spacecraft dodging dense asteroids are a convenient narrative fantasy, not a description of the real belt. The NASA OSIRIS-REx mission collected samples from the asteroid Bennu and brought them back to Earth in 2023. Preliminary analysis revealed the presence of hydrated minerals and organic compounds, including amino acids. This confirms that carbonaceous asteroids carry the chemical ingredients associated with life, and reinforces the hypothesis that asteroid bombardment in Earth's early phases may have delivered some of the organic material that contributed to the planet's prebiotic chemistry. The asteroid that could once have been a threat turned out to be a messenger carrying ingredients. The NASA DART mission, in September of 2022, deliberately crashed a probe into the asteroid Dimorphos and altered its orbit in a measurable way. It demonstrated for the first time that we have the technical capability to deflect an asteroid, an achievement that transforms planetary defense from theory into demonstrated practice. It's one of the most concrete ways in which knowledge of the solar system translates into the ability to protect life on Earth. Jupiter is the largest planet in the solar system by a considerable margin. Its mass is 2.5 times greater than all the other planets combined. With 318 Earth masses, it's an object of a scale that makes direct comparison with the rocky planets difficult. Jupiter is essentially a ball of hydrogen and helium, with no defined solid surface. As pressure increases toward the center, the gas gradually transitions to liquid and then to increasingly exotic states. Inside Jupiter, the pressure is so extreme that hydrogen takes on a form unknown on Earth, metallic hydrogen, a state in which electrons detach from nuclei and flow freely as in a metal, making hydrogen electrically conductive. That layer of liquid metallic hydrogen is responsible for the most intense magnetic field of any planet in the solar system, about 14 times stronger than Earth's. Jupiter's magnetic field creates a magnetosphere that would extend from Earth to beyond Saturn's orbit if it were visible to the naked eye. Jupiter's Great Red Spot is an anticyclonic storm that has existed for at least 350 years, since the first systematic telescopic observations of the planet. At its peak, it was twice the diameter of Earth. Today it's smaller and has been measurably shrinking over recent decades. What keeps a storm going for centuries without dissipating has to do with the absence of a solid surface on Jupiter. With no surface to dissipate energy, storms can persist. And the red color of the spot, caused by sulfur and phosphorus compounds, still doesn't have a completely definitive chemical explanation after decades of study. Jupiter has 95 known moons. But the four largest, Io, Europa, Ganymede and Callisto, are worlds in their own right, discovered by Galileo in 1610. Io is the most geologically active object in the Solar System, more so than Earth itself. Its surface is covered in active volcanoes that launch plumes of sulfur dioxide hundreds of kilometers into the sky, and the entire surface is continuously renewed by lava flows. Io has no visible impact craters. Any crater is quickly buried by volcanic activity. The source of Io's energy is not residual internal heat, but tidal heating, Jupiter's gravity, combined with the gravitational influences of Europa and Ganymede that keep Io in a slightly elliptical orbit, physically deforms Io in cycles of flexing that generate heat through internal friction. It's the same mechanism that may be responsible for maintaining liquid oceans beneath the surfaces of other moons, making them candidates for habitability in places that no previous model of the habitable zone would have predicted. Europa is, for many astronomers and astrobiologists, the most intriguing location in the Solar System in terms of potential for extraterrestrial life. Beneath its ice surface, estimated at 10 to 30 kilometers thick, there exists a liquid water ocean with a depth of 60 to 150 kilometers. The total volume of water in that ocean is estimated at twice the volume of all of Earth's oceans combined, beneath the surface of a moon with only 1/4 of Earth's diameter. In 2012, the Hubble Space Telescope detected plumes of water vapor rising from Europa's surface, possible evidence of water from the subglacial ocean reaching space. What makes Europa especially interesting for astrobiology is the possibility that the bottom of its ocean, in contact with the rocky mantle heated by tidal forces, could host hydrothermal systems similar to the hydrothermal vents on Earth's ocean floor. Those environments on Earth support complex microbial communities completely independent of sunlight. If the same is possible on Europa, it may have had habitable conditions that have existed for more than 4 billion years. Enceladus is one of the most surprising discoveries of modern planetary exploration, a moon just 504 kilometers in diameter that turned out to be geologically active and potentially habitable in a way no one had predicted. In 2005, the Cassini probe discovered plumes of water vapor and ice particles jetting from fissures at Enceladus's south pole at speeds of hundreds of meters per second, continuously feeding Saturn's E-ring with fresh material. Chemical analysis of the plumes revealed not just water and ice, but also carbon dioxide, methane, molecular hydrogen, salt, and complex organic compounds, including molecules with more than 10 carbon atoms. The presence of molecular hydrogen is especially significant. It's produced by hydrothermal reactions between hot water and rock, and it's an energy source used by chemosynthetic microorganisms on Earth's ocean floor. Enceladus has a liquid ocean in contact with a hydrothermally heated rocky floor, with chemistry compatible with sustaining microbial life, and that ocean is launching samples of itself directly into space. It's probably the most accessible environment in the Solar System for the search for life beyond Earth. Saturn is the most immediately recognizable planet in the Solar System. Its rings are visible even with a modest telescope. Galileo, upon observing it in 1610, was confused by what he saw. The telescope of the time didn't have enough resolution to distinguish the rings, and he described Saturn as a planet with ears. Saturn has a physical property that sets it apart from all other planets in the solar system. It's the only one with an average density lower than that of water. If there were an ocean large enough, Saturn would float. Saturn's rings extend up to 282,000 kilometers from the center of the planet, but are only 10 to 1,000 meters thick in most regions, a ratio of width to thickness comparable to a sheet of paper. They're composed mainly of water ice in particles ranging from microscopic grains to blocks several meters across. The Cassini mission, which orbited Saturn between 2004 and 2017, revealed that they're surprisingly young, only 100 to 400 million years old. Saturn's rings didn't exist when dinosaurs roamed the Earth. They were most likely formed by the destruction of a moon in a geologically recent period. Titan, Saturn's largest moon, is one of the most extraordinary worlds in the solar system. Its atmosphere is composed mainly of nitrogen, like Earth's, with about 5% methane. At that temperature of -179 degrees Celsius, methane plays on Titan the role that water plays on Earth. There's a complete methane cycle. Methane evaporates, rises into the atmosphere, condenses into clouds and falls as rain. The Huygens probe, which descended through Titan's atmosphere in January of 2005, photographed drainage channels and coastal structures that turned out to be rivers and lakes of liquid methane. Titan's atmosphere is rich in complex organic chemistry. Ultraviolet radiation from the Sun converts atmospheric methane and nitrogen into a thick haze of organic molecules that settles on the surface, creating a reddish layer of compounds that includes precursors to amino acids and nitrogenous bases. Titan's chemistry is, in a certain sense, a planetary-scale simulation of the prebiotic organic chemistry that may have occurred on early Earth, but frozen at temperatures that prevent the reactions necessary for life as we know it. It's like finding a chemistry lab in full operation, but without the heat needed for the experiments to complete. Uranus is the most underestimated planet in the solar system. The most notable of its features is its axial tilt of almost 98 degrees. Uranus effectively orbits the Sun on its side, with its rotation axis almost in the orbital plane. During a period of approximately 42 years, one pole faces the Sun continuously while the other remains in total darkness, an extreme seasonality with no parallel on any other planet. Recent simulations suggest that inside Uranus, methane may be compressed to the point where carbon atoms separate and precipitate as diamond crystals, a process called diamond rain, sinking toward the core. A rain of diamonds falling silently inside a frozen planet. Neptune is the most distant planet in the solar system, and also the windiest. Despite receiving only 1/900th of the solar energy that Earth receives, Neptune has winds that can reach 2,100 km per hour, the fastest of any planet. That energy doesn't come from the Sun, it comes from the planet's internal heat, which emits 2.6 times more energy than it receives. Neptune has a significant internal heat source that drives its dynamic atmosphere. Neptune has an extraordinarily unusual moon, Triton. Its largest satellite orbits in a retrograde direction, opposite to the planet's rotation. No large moon formed in place could have a retrograde orbit. Triton is almost certainly a captured object, most likely a large Kuiper belt body that was captured by Neptune's gravity. Triton is in a progressively decaying orbit. In approximately 3.6 billion years, it will come close enough to Neptune to be torn apart by tidal forces. The fragments will form a ring around Neptune that could be more massive and spectacular than Saturn's rings. It's an event scheduled for the geological future of the solar system that physics allows us to predict with confidence. Beyond Neptune's orbit begins a region of the solar system that remained completely unknown until 1992, the Kuiper belt. The Kuiper belt extends from approximately 30 to 50 astronomical units from the Sun and contains hundreds of thousands of objects more than 100 kilometers in diameter, and billions of smaller objects. The composition of Kuiper belt objects reflects their origin beyond the ice line. They're rich in water, methane, and ammonia ices, as well as rocky and organic materials. Each object is an archive of conditions in the outer protoplanetary disk, preserved in a cosmic freezer since the formation of the system. Pluto was discovered in 1930 and was considered for 76 years to be the 9th planet of the Solar System. In 2006, the International Astronomical Union reclassified it as a dwarf planet. NASA's New Horizons mission flew past Pluto in July of 2015, the moment when a blurry point of light in telescopes became a world with detailed geography. The images revealed a dwarf planet of surprising geological complexity, water ice mountains up to 3,500 meters high, plains of nitrogen ice in active convection, and a heart-shaped region, informally called Tombaugh Regio, which is one of the most visually striking structures in the outer solar system. Pluto's nitrogen plain is in slow convection. Cells of warm nitrogen ice rise from the interior, cool at the surface and sink back down, in cycles that last hundreds of thousands of years. This process is possible because solid nitrogen at temperatures close to its sublimation point is viscous enough to flow. It's a type of convection that exists nowhere else known, driven by residual internal heat from a world the size of a state, billions of kilometers from the Sun. Comets are the most visually dramatic objects in the solar system, and also some of the most scientifically valuable. A comet is essentially a nucleus of ice and rock, typically a few kilometers in diameter, that when it approaches the Sun heats up and sublimates, releasing gases and dust that form the characteristic coma and tails. Comets have two distinct tails, the dust tail, white or yellowish, formed by particles swept along by solar radiation pressure, and the plasma tail, bluish, formed by ionized gases swept by the solar wind, which points exactly in the direction opposite to the Sun, regardless of the comet's direction of movement. The ESA Rosetta probe, which orbited comet 67P between 2014 and 2016 and landed the Philae probe on its surface, revealed an irregularly shaped, bilobate nucleus covered in a dark crust of processed organic material. Chemical analysis revealed complex organic molecules, including glycine, an amino acid, and phosphorus, an element essential for DNA. Each comet is a unique object, with its own history and activity. And every comet that passes through the inner solar system carries chemical messages from regions that no probe has ever visited. Comets originate in two distinct regions of the solar system. Short-period comets, those that complete an orbit in less than 200 years, originate mainly in the Kuiper belt. Long-period comets, with orbits that take thousands or millions of years to complete, originate in a much more distant region called the Oort cloud, a spherical shell of icy objects extending from about 2,000 to 100,000 astronomical units from the Sun. The Oort cloud has never been directly observed, it's inferred from the orbits of long-period comets. Its outer distance, possibly 100,000 astronomical units, or almost 2 light-years, is so vast that it extends to almost half the distance to the nearest star. In a certain sense, the Oort cloud defines the gravitational boundary of the solar system, the limit beyond which the Sun's influence over primordial material is overcome by other forces. It's a boundary we'll never see directly, only through the frozen messages it sends back toward the Sun in the form of comets. In October of 2017, astronomers detected an object passing through the solar system on a hyperbolic trajectory, with excess speed to be gravitationally bound to the Sun. It was the first time an interstellar object had been detected passing through our system. Its official name is 1IA 2017 U1, but it was nicknamed Oumuamua, a Hawaiian word meaning messenger from afar arriving first. Oumuamua had characteristics that puzzled astronomers. Its apparent shape suggested a very elongated object, and its trajectory showed an acceleration beyond what solar gravity could explain, a deviation consistent with radiation pressure, but requiring the object to be extraordinarily thin and low in density. The most widely accepted interpretation today is that Oumuamua was a fragment of solid nitrogen material chipped from the surface of a dwarf planet in another star system. In 2019, a second interstellar object, Comet Borisov, passed through the system with more conventional behavior. Interstellar objects pass through the solar system more frequently than we imagined, we simply didn't have the telescopes to detect them before. The solar system is immersed in the interstellar medium, and in constant exchange of material with it. And there's a fascinating consequence of that exchange. Asteroid impacts on rocky planets can eject crustal fragments at speeds sufficient to escape planetary gravity and even the Solar System. Martian rocks reach Earth regularly. There are more than 270 meteorites identified as coming from Mars. If organisms can survive the journey, they could in theory transfer life between planets. The question of whether we are Martians is scientific, not just rhetorical. The Voyager 1 and Voyager 2 probes are the most distant human-made objects from Earth. Launched in 1977, both took advantage of a rare planetary alignment that occurs only once every 176 years to carry out a grand tour of the outer planets, using the gravity of each planet as a slingshot to the next. That window of opportunity was calculated by engineer Gary Flandreau in 1965, and the decision to take advantage of it resulted in one of the most successful scientific exploration projects in history. Both probes continue to operate and transmit scientific data, a remarkable feat for equipment more than 45 years old. Estimates indicate that the scientific instruments may continue operating until around 2025 to 2030, when the available power will be insufficient. After that, the Voyagers will continue their silent journey through the galaxy for billions of years, the only human-made objects that will almost certainly outlast any civilization that may exist on Earth in the distant future. The Solar System appears, at first glance, like a clockwork mechanism, planets in predictable orbits, moving according to fixed laws. And on timescales of centuries or millennia, that impression is correct. But on timescales of millions to billions of years, the Solar System is a chaotic system in the precise mathematical sense of the term. Modern computer simulations show that the orbits of the inner planets, especially Mercury, become unpredictable on scales of a few tens to hundreds of millions of years. There's a small but non-zero probability that Mercury will enter a chaotic trajectory in the next 5 billion years. The Solar System is stable enough that life has had time to evolve, but it's not the perfectly ordered, perpetual mechanism that intuition suggests. Orbital resonances are one of the most elegant phenomena in solar system dynamics, patterns of motion in which the orbital periods of two or more bodies are in simple integer ratios. Jupiter's Galilean moons display one of the most famous resonances in the solar system. Io, Europa, and Ganymede have orbital periods in the exact ratio of 1 to 2 to 4. For every 4 orbits of Io, Europa completes exactly 2 and Ganymede exactly 1. This Laplace resonance keeps the orbits of Io and Europa slightly elliptical, which is necessary for the tidal heating that keeps Io volcanic and possibly Europa with a liquid ocean. Without the Laplace resonance, the orbits would be circular, tidal heating would be minimal, and two of the most potentially interesting worlds in the solar system would be frozen and geologically dead. The habitability of Europa depends on a simple numerical ratio between the orbital periods of 3 moons. Planetary migration, the movement of planets to orbits different from those of their formation, is one of the concepts that has most transformed our understanding of the solar system's history over the last 3 decades. The evidence for that migration exists in multiple places simultaneously: the isotopic composition of meteorites, the structure of the asteroid belt, the distribution of objects in the Kuiper belt. Planetary migration is not an auxiliary hypothesis, it's necessary to simultaneously explain multiple independent features of the system. The habitable zone, the range of distances around a star where a rocky planet could maintain liquid water on its surface, is one of the most widely used tools in the search for potentially habitable planets. For the Sun, that zone extends approximately between 0.95 and 1.67 astronomical units. But the conventional habitable zone is a simplification. Venus demonstrates that being in the habitable zone doesn't guarantee habitability. Mars demonstrates the inverse: it may have been habitable in the past despite being close to the outer limit. And the oceanic moons of Jupiter and Saturn demonstrate that habitability can exist completely outside the conventional habitable zone. Robotic missions to the solar system have produced some of the most transformative scientific moments in recent history, and also some of the most poetic. The pale blue dot photograph, taken by Voyager 1 on February 14, 1990, at the request of astronomer Carl Sagan, shows Earth as a tiny point of light in a scattered ray of sunlight, a fraction of a pixel in an immense universe. The image was taken when the probe was 6 billion kilometers away, and Earth occupies less than 1/10 of a pixel in the photograph. The image symbolized something that space exploration made concrete in a way that no abstract argument can: the fragility and uniqueness of the planet we inhabit. In all the expanse of the solar system visible in the photograph, with its planets, asteroids, comets, and vast space, the only place we know to contain life is that almost invisible point. Every war, culture, achievement, and tragedy of humanity has taken place on that fraction of a pixel. But the same exploration that produced that humbling perspective also revealed that the solar system has other worlds with potentially habitable conditions: subglacial oceans, organic chemistry, energy sources. The image of a single habitable point may be incomplete. And if other worlds in the solar system have life, it never knew that Earth existed. The fate of the solar system on geological and astronomical timescales is a fate that physics can outline with reasonable confidence. Over the next 1 to 2 billion years, Earth will most likely lose its oceans. The increase in solar luminosity will intensify the greenhouse effect to the point of triggering an irreversible evaporation process. Life on Earth, if it survives, will need to have adapted or migrated. In 5 billion years, the Sun expands as a red giant, and the inner solar system is radically transformed. The frozen moons of Jupiter and Saturn, currently below 0 degrees, could temporarily have liquid water on their surfaces. The habitable zone of the solar system will migrate outward. After the giant phase, the Sun becomes a white dwarf, and the surviving planets continue orbiting in silence around an ember that grows progressively dimmer. It's a quiet end for an average star, and also the fate of the only solar system we know to have produced beings capable of contemplating that end. There's something deeply meaningful in the fact that the same solar system that produced Earth also produced Jupiter with its subglacial oceans on moons, Saturn with its ephemeral rings, Pluto with its convecting nitrogen plain, and Enceladus with its ocean plumes launched directly into space. Each of these worlds operates according to the same physical laws as Earth, but applies them under conditions so different that the results are unrecognizable from one to the other. That diversity within a single star system is the most compelling argument we have that physics applied to different initial conditions produces a variety of worlds that no imagination could have anticipated. And if the solar system, with its single star, its 8 planets and its hundreds of moons, already displays that richness, what can we expect from a galaxy with 100 to 400 billion stars, each with its own system, across 13.8 billion years of history? The exploration of the solar system is, ultimately, the beginning of a much broader understanding of what the cosmos can contain. Every mission that lands on an asteroid, orbits a gas giant, or crosses the heliopause expands not just scientific knowledge, but the scale of what we consider possible. The solar system has taught humanity that worlds are more varied, more complex, and more surprising than any model predicted. And that lesson, that reality systematically exceeds imagination, is perhaps the most important one that space exploration has ever produced. You exist because a cloud of gas collapsed in the right place, at the right time, with the right ingredients. Because a snow line divided the protoplanetary disk in the right place. Because Jupiter danced in the right direction. Because an asteroid delivered water from a distant region. Because a protoplanet called Theia collided at an angle that created the Moon instead of destroying the Earth. Each of those events was contingent. None of them was inevitable. And all of them happened. As these ideas settle in, as the vastness of the solar system begins to feel not distant, but familiar, let your body sink a little deeper, and allow the silence between the planets, the same silence that exists between Saturn and its rings, between Enceladus and its hidden ocean, to also be the silence within you right now. And as you drift into a deep and restful sleep, remember to subscribe, so these stories can keep finding you, night after night. Sleep well, and sweet dreams.